Next topic is prime and theorems on prime numbers. That is Euclid's lemma. And here is the definition of prime numbers. A non-zero integer p not equal to plus minus 1. That is plus minus 1 are not primes. Is called prime. That is first note that plus 1 and minus 1, these two are not prime numbers. Is called prime if it has no divisor other than plus minus 1 and plus minus p. That is the numbers divisible by itself and 1 are called prime numbers. And we know the definition of divisibility. If you find the divisors of suppose 7, then what are the divisors of 7? 1 is the divisor of 7 and 7 itself is the divisor of 7. Also minus 1 and minus 7 are divisors of. That is 7 has only divisors plus minus 1 and plus minus 7. That's why 7 is a prime number. So we know the divisors. For example, if you take 8 number, then what are the divisors of 8? 2 divides to 8. 1 also divides to 8. Why 2 divides to 8? Because 8 expressed in the form 2 into 4. For some integer 4 belongs to 0. But 2 does not divide to 9. 2 is not divisor of 9 because 9 does not express in the form 2 into some integer. This 4.5 number exists. That 2 into 4.5 is 9. But this 4.5 is not integer. That's why we say 2 does not divide to 9. Also minus 2 divides to plus 8. Also 2 divides to minus 8. We know these notations or this relation that divides. 3 divides to 15. So what are the divisors of suppose 8? The divisors of 8 are plus minus 1. Then plus minus 2, then plus minus 4 and plus minus 8. And that's why 8 is not prime number. So when the number is called prime number, if it has no divisors other than plus minus 1 and plus minus 2. That is only these two are called proper divisors. Improper divisors. What are the these are called improper divisors. And what are the proper divisors? Suppose 8. What are the divisors of 8? Plus minus 1 and plus minus 8. These are divisors of 8 are called proper divisors. Improper divisors, not proper divisors. And what are the proper divisors of 8? Plus minus 2, plus minus 4. These are called proper divisors of 8. So when another definition of another form of the prime numbers, that when we say integer or number is called prime number, if it is an integer, first it is an integer and which has no proper divisor. Why 8 is not prime number, prime integer? Because 8 has a proper divisor. What are the proper divisors of 8? Plus minus 2 and plus minus 4. And what are the improper divisors of 8? Plus minus 1 and plus minus 8. And if you consider 2, then what are the divisors of 2? Plus minus 1 and plus minus 2. So 2 is prime. Plus 2 or minus 2, both are prime. Plus minus 3, plus minus 5, plus minus 7, plus minus 8 is not prime because 8 has a proper divisors, or 8 has a divisors plus 2, minus 2, plus 4, minus 4. Okay. 9 is also not a prime number, prime integer. Because why 9 is not prime integer? Because 9 has a proper divisors. What are that? Divisors of 9, proper divisors of 9, plus minus 3. 3 divides to 9 as well as minus 3 divides to 9. And that's why 9 is not proper, is not prime integer. Okay. Then 10 is not prime integer. 11 plus minus 11 is prime integer. Okay. Or prime number. Because what are the divisors of 11? Itself 11 plus minus 11 and plus minus 1. 11 has no proper divisor. This is not the list of odd numbers or even numbers. This is not the list of 2, 3, 5, 7, 9. There is no 9. That is, this is not the list of odd numbers or even numbers. Okay, this is the list of prime integers or prime numbers. So when we say the number is called prime, if it has only 2 divisors, itself and 1. Okay, this is a very simple definition of prime numbers. So if we express the number in this form, then we say it is a canonical form of that number. For example, 100. 100, if we express 100 as a product of primes, express 100 as a product of primes. So 2 into 25, okay. First write 2 into 50, then 2 into 25, and then 5 into 5. Okay, this is the procedure of writing this 100 as a prime. That is, we write product of prime, and that is 100 as 2 raised to 2, 5 raised to 2. Don't write this 3 raised to 0. No need of this 3 raised to 0. So this is what? This is in this form. What are P1, P2, PR? These are primes, distinct primes. Okay, that is important. And alpha I is what? Greater than or equal to 0. So this is the canonical form of 100. That is, this is the factorization of 100 as a product of primes. And this is the factorization of this 6750 as a product of primes. And so we write this as 2 raised to 1, 3 raised to 3, 5 raised to 3. And 7 raised to 0. Don't write this 7 raised to 0. No need of this 7 raised to 0. Okay. So this is the canonical form of 6750. So we can express the number in canonical form. And we can find the greatest common divisor by using canonical form. Already we observed the example of greatest common divisor by using factorization as a product of primes. For example, the greatest common divisor of 100 and 6750 is what? So take the common factors. So what are the common factors? Here is 2 raised to 2, here is 2 raised to 1. 2 is common, so take 2. And here is 5 square, here is 5 cube. So 5 square is common. So another factor 3 is not common. Okay, 3 raised to 0. Here is 3 raised to 3, but here is 3 raised to 0. There is not 3. That is 2 into 5 square. What are the common? 2, 5, and 5. And so multiplication is what? Multiplication is 50, and therefore greatest common divisor of 100 and 6750 is what? Is another method to find the greatest common divisor. For example, this is the example that express this 540 and 126 as in a canonical form. That is, express this number 540 and 126 as a product of positive primes. 197. That express in canonical form or express as a product of primes. Both the meaning of the both is same. That is, express. We have to express these numbers as in canonical form means we have to express these numbers as a product of primes. So first take 5 and then find greatest common divisor. Okay. So first number is 540. So 2 into, so first divide by this number by 2. Then divide this number by primes. First divide by 2. If 2 is not divisor of this, then take 3. If 3 is suppose not divisor of this number, then take 5. Don't take 4, because after 3, what is the prime number? 5. If 5 is not divisor, suppose, then take what? 7. Don't take 6. Okay. And then if 7 is not divisor, suppose, of this number, then take 9. So continue this procedure. Take first smallest number. If 2 is not divisor, then take 3. 3 is not divisor, then take 5 here. Okay, but 2 is divisor of this number. So 2 into 7, 270. Then again divide this number 270 by 2. If 2 is not divisor, then take 3. 3 is not divisor, then take 5. Okay, so 2 into 135. Then divide this number 135 by 3. If 3 is not divisor, suppose 135, then take 5. But 3 is divisor, then 45. Then divide 45 by 3. Okay, 3 is divisor. If 3 is not divisor, then take 5. But 3 is divisor. So 3 into 15, then take 15. Divide this 15 by 2 first. Here we divide this number 135 by 2. But 2 is not divisor, then take 3. If 3 is not divisor, then take 5. Don't take 4. Then 15. 3 is divisor. Okay, and then 3 into 5 is 15. And therefore, what is the canonical form of 540? 2 raised to 2, 3 raised to 3, and 5 raised to 1. This is canonical form of 540. And what is the canonical form of 126? That is, divide this 126 by 2, 63. Then divide this 63 by first 2, but 2 is not divisor. Then take 3. Divide by 3. Then 3 into 21. Then divide this 21 by first 2, but 2 is not divisor. Then take 3. 3 into 7. And then 2 raised to 1 into 3 raised to 2 into 7 raised to 1. This is the canonical form of this number. Right, into sign between these. And then what are the common factors? 2 is the common factor and 3 square is the common factors. 3 square. and therefore 2 into 3 square, that is 18, is the greatest common divisor of these two numbers. So next is Euclid's lemma. This is a very important theorem as far as exam concerned. So what is the Euclid's lemma? What is the question on this theorem? That state and prove Euclid's lemma. So what is the question? If P is prime and A and B are integers such that P divides to AB, this is given that P divides to AB, then prove that what is to prove? Then prove that either P divides to A or P divides to B. What do I have to show? P divides to A or P divides to B. So what is given? P is prime is given, A and B are integers given, and A divides to AB, this is given, and we have to show either P divides to A or P divides to A. So I assume that P is prime and P divides to AB. We assume that AB are integers and P is prime. Then P divides to AB implies AB is equal to AB expressed in the form P into some integer, P into K or K into P, right? P into K or K into P. Okay, because AB divides to P divides to AB. This is given, and P divides to AB. Therefore, AB expressed in the form P into some integer for some K belongs to J. And now we have to show either P divides to A or P divides to B. So when this statement P divides to A or P divides to B is true, the two statements are joined by OR conjunction, connective, logical connectives is OR, and we know the table of P or Q. Okay, table of OR. When the statement P or Q is true, if one of them is true, and when if the statement is joined by AND, then when the statement is true, that compound statement is true, if both are true. But here is the two statements, P divides to A and P divides to B are joined by OR. Then when this is the compound statement or this combined statement is true, if one of them is true, okay, and if both are true, then also true, but one of them is true, then this total whole statement is true. So if I assume P divides to A, then there is nothing to prove, then theorem is obvious, that is P divides to A. If I assume P divides to A is true, then this statement obviously proves that P divides to A or P divides to B, because when P divides to A or P divides to B is true, that is the statements, the two statements are joined by or R, and when this is true, if one of them is true, that is if we assume P divides to A, then the theorem is obvious, then there is nothing to prove, and so assume that P does not divides to A. So assume that P does not divides to A, because if we assume P divides to A, then there is nothing to prove, then theorem is very obvious. So assume that P does not divides to A. If P does not divides to A, so that's the second case. Then what happened? The greatest common divisor of P and A is 1. Why this greatest common divisor of P and A is 1? Because what is the greatest common divisor? How we can find the greatest common divisor of P and A? This method. That first find the divisors of P. What are the divisors of P? Plus minus 1 and plus minus P, because P is prime. So P has only 4 divisors that are okay. We find greatest. We have to find greatest common divisor. That's why we find only positive divisors of these two numbers. So what are the positive divisors of P? So if you find the divisors of P, positive divisors of P, then what is the list of that divisors? Is only 1 and P. These are only the two positive divisors of P, because P is prime. What is the definition of prime? That the number is called prime if it has only divisors plus minus 1 and plus minus P. Another number does not divide to P. Okay. So what are the divisors of P? 1 and P. Only these are the two positive divisors of P. And what are the divisors of A? So what are the divisors of A? The least of the divisors of A, first number of the least of the divisors of A is what? 1. Because 1 is divisor of every number. Okay. And then last number is A in that list. Last number in that list of the divisors of A is A. So what are the middle numbers? We don't know all the middle numbers, because we don't know A, exact value of A. So the first only, but we have to take the greatest common divisor of P and A. Means we have to find the common divisors of P and A. So what are the divisors of P, 1 and P? So 1 is common divisor in between P and A. So and another divisor of P is only P. So P is divisor, if the P is divisor of A, in the list of the divisors of A, if we have P, when P is, belongs to the list of the divisors of A, if P is divisor of A, but P is not divisor of A, and that's why this list of the divisors of A does not contains P, and therefore the common divisor of P and A is only 1. That is the greatest common divisor of P and A is 1. So the greatest common divisor of P and A is 1. Okay, because the common divisors of P and A are what? Only 1 is the common divisor of P and A. Because what are the probability of the greatest common divisor of P and A? The least of the divisors of P is only contains 2 elements, 1 and P. And we don't know the least of the divisors of A. But the probability of the greatest common divisor of P and A is what? Is either 1 or P. Because what is the meaning of greatest common divisor of P and A? The common divisor of P and A. So P has only 2 divisors, positive divisors, that are what? 1 and P. And so what is the common divisors of P and A? Either P or A, either 1 or P. Only the probability of the greatest common divisor of P and A is what? 1 or P. But when P is the greatest common divisor of P and A, if P divides to P, yes, P divides to P. But when we say it is common divisor if P divides to A, but here P does not divides to A, and therefore greatest common divisor of P and A is only 1. Probability are 1 or P, but P is not greatest common divisor. That's why 1 is greatest common divisor. Okay, that because P is prime and P does not divides to A, therefore greatest common divisor of P and A is 1. This is very important result after this P does not divides to N. And as a PA is equal to 1, and therefore there exists X and Y such that integers X and Y belongs to Z such that 1 is equal to Px plus Ay. This is the theorem, previous theorem. That is, if the greatest common divisor of two integer is suppose D, then D expressed in the form Ax plus By. Okay, that's why 1 is the greatest common divisor of P and A, and therefore there exist integers X and Y such that 1 is equal to Px plus Ay. Okay, multiplying the both sides by using P. What do we have? B is equal to Pxb plus Ayb. Then B is equal to P, right? X into B in bracket, and here write AB in bracket Y. Then what is the value of AB? That P divides to AB is our assumption. Therefore, AB is Kp or Pk. So write that's AB as Pk into Y as it is, because by using assumption. By using this equation, AB is equal to Pk, like AB is equal to Pk, and then what do we have? B is equal to P. Take this P as common. So what do we have in bracket? Xb plus Ky, and this Xb plus Ky is integer, because write here comma and then write where Xb plus Ky belongs to Z. Here write one more sentence. And why this Xb plus Ky is integer? Because all X, Y, B, K are integers. All are 4 are integers, and multiplication and addition of integer is integer. And therefore B expressed in the form P into some integer, and therefore P divides to B. So if we assume P does not divides to A, then we have P divides to B. That is, if this is not true, then this is true. If this is true, if P divides to A, then the theorem is obvious. If this is not true, then this is true. That is ultimately this statement that P divides to A or P divides to B is true, because one of them is true. And therefore, if P does not divides to A, then we have P divides to A, right? Does not divides to A in this part. And therefore, theorem that if P divides to AB, then either P divides to A or P divides to B. This proves theorem. Here, with the generalization of the above theorem, we take as a corollary that generalization of the above theorem. That is, if P is prime and P divides to A1, A2, AN, here is only two, that A1 and A2. AB means A1 and A2. Suppose here are two, product of two. Here is product of suppose n integers, that P is prime and P divides to A1 into A2 into AN. Then what we have to show? Then we have to show P divides to one of them, either A1 or A2 or A3 or AN. That is, then we have to show, then prove that P divides to AI for at least one I runs from 1 to N. That is, P divides to one of them, at least one of them. And we prove the result by mathematical induction on N. Suppose that is the first mathematical induction, first form of the mathematical induction. We prove the result is true for either 1 or 2 or 3. Suppose n is 2. Then what do I have to prove? We have to prove if P divides to A1 into A2, then either P divides to A1 or P divides to A2. And this is very obvious by using previous theorem, that if P divides to A into B, then P divides to A or P divides to B. And so this is true, that if P divides to A1 into A2, then either P divides to A1 or P divides to A2. Already this is by using Euclid's lemma. So just write here, don't write proof, just write that by Euclid's lemma, or by it is true by above theorem, that if P divides to AB, then P divides to A or P divides to B. So if n is 2, then we have to prove the theorem as P divides to, if P is prime and P divides to A1 into A2, then P divides to either A1 or A2. But this is very obvious by using above theorem by Euclid's lemma, that if P divides to AB, then either P divides to A or P divides to B. So P divides to A1 into A2, then either P divides to A1 or P divides to A2. So just write that theorem is true for n is equal to 2. This is the first step of the mathematical induction. Then in second step, we assume that the result is true for n is equal to k. That is what is our assumption, that P is prime and P divides to A1, A2, AK. That is substituted as k. Then P divides to AI for at least one I runs from 1 to k, right here as k. So this is our assumption. It's called induction hypothesis, and we have to show the result is true for n is equal to k plus 1. That is what we have to show. If P is prime and P divides to A1, A2, A3, AK plus 1, right? N as k plus 1. Then P divides to AI for at least one I runs from 1 to k plus 1. This is we have to prove. Here is right. If P divides to A1, A2, AK, P divides to, what is assumption? That suppose P divides to A1, A2, AK plus 1, that is substitute n as k plus 1. Then we have to prove, what do we have to prove? Then P divides to one of them. That is P divides to AK plus 1. P divides to one of them. So how we prove? This P divides to A1, A2, AK plus 1 implies P divides to A1 into A2 into AK or P divides to AK plus 1 by using the above theorem, means by using Euclid's lemma. So consider A1 into A2 into AK as one number, suppose A. The product of these two, all number is suppose A and this is B. Then what do we have to show? Then what we have, that P divides to A into B, and therefore above theorem P divides to either this number, that is A1 into A2 into AK, or P divides to AK plus 1 by using the above theorem, that this theorem, that if P divides to AB, then either P divides to A or P divides to B. Okay, we have this by using above theorem. And if P divides to AK plus 1, then what happens? AK plus 1, then I is equal to k plus 1. That I, we have to find the value of I, that I is k plus 1. And suppose if P does not divides to pk plus 1, suppose this is true, that P divides to A1 into A2 into AK, then by induction hypothesis, that is our assumption is that if P divides to A1 into A2 into AK, then P divides to one of them from I runs from 1 to k. Then if P divides to A1 into A2 into AK, then by induction hypothesis P divides to AI for at least one I runs from 1 to k, and therefore we have combined these two statements, that P divides to AI for at least I runs from 1 to k plus 1. That is, the result is true for k plus 1. So in second case, we assume the result is true for k, that is we assume this p divides to a1 into ak, then p divides to one of them, and we assume p divides to a1 into a2 into ak plus 1, and we have to show the p divides to one of them. But we consider this a1 into a2 into ak as one number. Suppose this is a and ak plus 1 as b. And what is the above theorem? Euclid's lemma, that p divides to a into b, then p divides to a or p divides to b. But we have p divides to a1 into a2 into ak or p divides to ak plus 1. Suppose this is true, that p divides to ak plus 1, then the theorem is true for n is equal to k plus 1. But if it is, suppose this is not true, that is, suppose p divides to a1 into a2 into ak, then what if one of them is true? One of them is true. This is true or this is true. If this is true, then the theorem is true. If this is true, then by induction hypothesis, p divides to one of them. That means p divides to a1 or a2 or ak plus 1. And that is the result is true for n is equal to k plus 1. And so by mathematical induction, we say the result is true for all natural numbers, all n greater than or equal to 1. So this is also important theorem, but previous theorem, this theorem is most important, that Euclid's lemma. Then the examples on the Euclid's lemma are similar to Euclid's lemma. That is, the greatest common divisor of b and c is 1, and a divides to b, then we have to show greatest common divisor of ac is 1. So greatest common divisor of this is given, and this is to show. So greatest common divisor of b and c is 1, means there exist two integers x and y such that one expressed in the form bx plus cy. This is by using the previous theorem. Okay, if greatest common divisor of b and c is 1, therefore one expressed in the form bx plus cy for some x and y belongs to z. Again, a divides to b implies b expressed in the form a into k for some k belongs to z. So this is given. And now we have to show AC is equal to greatest common divisor of AC is equal to 1. So when greatest common divisor of AC is 1, if one expressed in the form a into some integer plus c into some integer. So for that, putting this value of b in this equation number 1. So what we have, 1 is equal to ak x plus cy, and then take this, write this aks as a kx plus cy, and obviously this kx and y are integers, and so one expressed in the form a into some integer plus c into some integer, and therefore 1 is equal to greatest common divisor of a and c is 1. The reverse use of the theorem, that the greatest common divisor of a and b is 1 is d if and only b expressed in the form ax plus cy. Same type example, the greatest common divisor of a, b is 1, and a divides to c and b divides to c, then we have to show ab divides to c. So what is given? Greatest common divisor of ab is 1. So there exists two integers x and y such that 1 is equal to ax plus by. That is 1 expressed in the form ax plus by. And a divides to c implies c expressed in the form a into some integers, k1. B divides to c means c expressed in the form b into some integer k2. Okay, so these 3, 1, 2, 3 are the meaning of our given. This is given. This is given in the theorem, that greatest common divisor of AB is 1. It means that this A divides to C means we have C is equal to AK1, and greatest B divides to C means C expressed in the form BK2. This is the given. And what we have to show? AB divides to C. So when AB divides to C, if C expressed in the form AB into some integer, so multiplying the equation 1 by C, what do we have? C is equal to ACX plus C, or CAX plus CBY multiplied by C, equation 1. And then write this value of C as BK2 here, and value of C is AK2. Don't write here both these AK1 and BK2. AK1 and BK2 are both the values of same C, but here write value of C in terms of BK2. Don't write here A. Then we get A square, here B square. We have to express C as AB into some integer. So here is write value of C in terms of B, that is BK2, and here write the value of C as AK1, and then take this AB as common. Then we have K2x plus K1y, and obviously this K2x plus K1y is integer. So C expressed in the form AB into some integer, and therefore we say AB divides to C. That AB divides to C. So similar problems we'll see in the next lecture.